Edexcel Further Maths Core Pure 1, Specimen Paper, Question 3. This is a polar curve, and we've got various sections of it shaded in, so it looks like it's going to involve the integral of a polar curve to find the area. We're given the equation of the curve, r equals sine theta over 6, and we also have here the region of values of theta, so we have a domain for theta, 0 to 6 pi. It's worth thinking at this point what that means in terms of the values of r. It means that we'll have values from sine of 0 over 6 to sine of 6 pi over 6. In other words, sine 0 all the way to sine pi. That means we're dealing exclusively with positive values of r, and r is going to start at 0, increase until it gets to a size of 1 at its greatest, and then decrease until it gets back to 0. So if it helps, a quick sketch of an ordinary sine graph between 0 and pi will give you a sense of what this function is doing in terms of the numbers we're going to get at different points. That's crucial for understanding a question like this, because we need to know which parts of this curve are drawn when in order to effectively answer a question about the area. Predictably enough, part A asks us to use algebraic integration to find the area of the coloured sections of the logo. These two parts here that have been shaded grey, they're the bits we need. The next part of the question uses a bit of creative thinking to answer a modelling question, really. We're talking about what happens if the logo gets scaled up, and we're going to use some tins of paint to cover it. So the key section here that we need to get right is the integral so that we can get the correct area for this curve. To do that, we need to be able to visualize what's going on. So we'll start at the very beginning, and we'll think about what happens when theta equals 0 and what happens as theta increases. Because theta is increasing from 0 to 6 pi, you can imagine a ray line starting pointing in the same direction as the initial line, but then rotating around, not just one complete turn, but 3 complete turns. And as it goes, r will change, and the curve will be traced out as r changes. So at the beginning, we know r is 0. And then as theta increases between 0 and pi, so the first half turn, it must be tracing out this first little section of the curve, because r is going from 0 to, well, it'll be sine of pi by 6. So in fact, we even know the value here, sine pi by 6 is a half. So this must be a distance of a half from the pole. That happens in the first section, from 0 to a half, and then it's going to continue to increase, as we know, all the way up to sine of pi by 2. In other words, sine of 3 pi by 6. So from pi to 2 pi, we're tracing out this section of the curve. From 2 pi to 3 pi, we're doing this. It's still increasing because we've got 2 pi by 6, which is about 0.866 root 3 over 2, all the way to 3 pi by 6, which is sine pi by 2, which is 1. This is the greatest possible distance from the pole. And then as we continue, we're doing the mirror image. So as sine goes from its maximum back down to the root, we go all the way down through this section between theta equals 3 pi and theta equals 4 pi. Then it sort of crosses over itself, goes into here between 4 pi and 5 pi. And finally, between 5 pi and 6 pi, it comes back to 0 again. Once you can visualize that, it's a good idea to keep in your head this sort of pattern as we move along. So if you can hold in your head what's happening with that, or if you can annotate on the curve exactly what's going on, then it'll help you to keep clear exactly what we need. Now, to find the area for something like this, we also need to have a good picture in our heads of exactly what the area formula does for us. It's all well and good to have the area formula memorized. So half r squared theta gives you the area of a sector. And when we integrate, we're essentially doing that same thing. We want half of r squared d theta because we're taking the area of some infinitely thin sectors. This is different to ordinary integration you might do with dy and dx, because in those cases you're thinking about the area of an infinitely thin rectangle with a height of y and a width of dx. Remember, when we're dealing with polar curves, we're thinking of the area of an infinitely narrow sector of a circle, where we know the area of the sector of a circle when theta is measured in radians will be half r squared theta. R theta is just going to be d theta a tiny sliver of theta, but we still have the half r squared in there. And depending on what our limits are, we'll have an a and a b value in there as well. We'll get to that in just a moment. But first, we need to visualize the integral. So the best way to do that is to imagine a tiny sector of a circle with the same radius as the point you're at that is being swept out as you go around the circle. So I've done this just by imagining a point that's slightly ahead, like 0.2 radians ahead of this point, so that we can visualize that bit being swept out. And you can see that unlike with ordinary integration, the area being swept out here is always relative to the pole, and we need to consider each part as if it's a small piece of a circle. So that's really important. If you watch this first section between theta equals 0 and theta equals pi, for instance, as we go along here, we are tracing out the entire first little section. So you can use that idea to work out exactly which sections will be traced out at different points, and that will help us to understand how we can get the shaded section. If you watch this go, the next section between pi and 2 pi, that traces out something that looks like it still includes a bit of this middle love heart part, but it also includes a large section of this rounder section here. And then if we continue between 2 pi and 3 pi, we now get information about the outer curve. And if we continue from 3 pi, we'll get the same thing all over again. So we'll get the outer curve. We're just doing the same thing, but in the opposite order. And then we get the middle curve, if you like. And then finally, we get the inner curve. But you'll notice that when we're tracing out the outer curve, it also includes the area of everything within it. So it's not just that it's giving us the shaded area between one bit of a curve and the bit below. It's giving us the entire thing. So as we get to this section here, I'm going to pause there. Any area you calculate within this region will calculate the area as if this is centered at 0, and it will include some of the area of the middle section and some of the area of the inside section. So once you've got that clear in your head, you want to maybe make a diagram. I've got something pre-prepared for this. As theta varies between 0 and pi, we're going to trace out this red area here. As theta varies between pi and 2 pi, we're going to get this green area, which you'll notice also includes a part which would be inside that smaller section. But then between 2 pi and 3 pi, we get this entire top half of the outer shape. And that overlaps with the two parts in the middle as well. So from that, we want to try to build for ourselves a way of constructing the total area. Let's give these things names. Let the red region be R for the sake of argument. Let's have the green region be G. Let the blue region be B. Now once we've got these, we can start to build up for ourselves the shaded area. Notice for a start that you can get the inner bit just by having two lots of R. We'll focus perhaps on just half the area to start with and then double it afterwards, but make sure if you do that, that you do double it. And the reason I'm going through this now before I integrate is that typically if I dive into the integration, I'll get an answer at the end and I'll say, great, I'm done, and I'll finish without thinking about whether I've combined all the areas properly. If I set out how I'm going to combine them at the beginning, that's where my focus is, and then I can do the integral afterwards without worrying. So I want this piece, but then I don't particularly want the green part, but then I do want a part which is not quite the blue bit, but it's effectively the blue bit minus the green bit. So if we think about that, the shaded part in this outer region is equivalent to the blue section minus the green section. The green section automatically takes into account whatever the red bit would be that's being overlapped. So this blue bit here, if we subtract the green bit that you can still see underneath it, that would give us exactly the shaded area from the large crescent moon shape. And then we just need to add on the red bit to get the total shaded area of that half. So we'll have the red part, and we'll have the blue part minus the green part. And then because that gives us just half of it, we're going to double the whole thing. Now we've got a clear idea in our heads of what we need to do, where the regions are we need to integrate, we'll come back to our integral and start calculating. So we have the formula that's given in the question as sine theta over 6. And we already know the limits that we're interested in dealing with here, but we're going to start perhaps by making a generic one that goes from a to b so that we can use the same indefinite integral to calculate the three definite integrals that we're trying to find. So instead of r squared, we're going to have sine squared theta over 6. Now this is not a complicated integral. This is an integral that you could have done at A-level maths, but it is one that requires a little bit of a trick. You have to remember the trick. If you're dealing with sine squared or cos squared theta somewhere, remember that it's not straightforward to integrate in that form, but it is straightforward to integrate sine of, say, theta over 6 or sine of 2 theta or something like that. So we're going to make use of the double angle formula for cos. If you recall, cos 2 theta is equal to cos squared theta minus sine squared theta. And if you don't remember that off the top of your head, you can look it up from the formula book. You have to do a little bit of work for it. They don't just give you it directly in that format, but they do give you cos of a plus or minus b is equivalent to cos a cos b minus or plus sine a sine b. So you can generate that for yourself by replacing sine and cos. Replacing a and b with theta in both cases. Once you've got that, we have our cos 2 theta formula. But what I particularly want is a way of replacing sine squared with something that only involves multiple angles instead of squared trig functions. So we can generate the alternative variant. Cos 2 theta can be written either exclusively in terms of cos squared or exclusively in terms of sine squared, because sine squared and cos squared are interchangeable provided we use the sine squared plus cos squared equals 1 identity. We can find a way of swapping one out for the other one. In this case, if we replace cos squared theta with 1 minus sine squared theta, we end up with 1 minus 2 sine squared theta. Once we have that, we can rearrange it a little bit so we can produce sine squared theta equals 1 minus cos 2 theta over 2. Or, more pertinent for our particular situation, sine squared of theta over 6 has to be equal to 1 minus cos of 2 lots of theta over 6, in other words, theta over 3, all over 2. That is going to be particularly helpful for us when we're trying to calculate this integral. So now we have this integral, but we can replace the whole of sine squared theta over 6 with this. One thing I will often do at this point, if I've got some messy fractions involved, is pull them out. So instead of 1 minus cos theta over 3 over 2, I'll just have 1 minus cos theta over 3. The over 2 can be pulled out because it's just a constant, so it's not going to be affected by the integration. That leaves me with a simpler process. I have a quarter of. Now in here, I just need the integral of 1 minus cos theta over 3. 1 integrates to theta, and cos integrates to sine, so I'll get sine of theta over 3. But because it's not just theta in there, it's theta over 3, I need to divide by the derivative of theta over 3. This is essentially the mini reverse chain rule. Dividing by a third is equivalent to multiplying by 3. So I'll put a 3 sine theta over 3 there. Because this is effectively definite integration, just between whichever particular limits I want at this point, I'm going to have an a and a b in there. Now I can calculate the three specific integrals I was interested in, which was these three here. I'm not going to bother with the diagrams for now. I've done the hard work of figuring out exactly which bits I want. I can now say that r is equal to this, but with a 0 and a pi. I can generate an expression for g in the same way. This will be between pi and 2 pi. And finally, B, the blue region, will be the same definite integral, but between different limits, 2 pi and 3 pi. Now I just need to evaluate those. And I want to make sure I've got nice exact values, but luckily most of these work out quite pleasantly, and if I need to, I've got a calculator I can refer to. So R becomes a quarter of, I'm going to keep the square brackets in, but I'm going to have two separate terms in here, one when I sub in pi and one when I sub in 0. So if I get this stuff and I put pi into it, I will have 3 sine pi by 3. But if I sub in 0 into the other one, I'm just going to get a 0. It's small enough to see. Because I get 0 for that bit, and sine of 0 over 3 is still 0. So that makes things a bit nicer here. You get a quarter of pi minus 3 sine pi by 3. Well, we'll keep the pi there, but sine pi by 3, because pi by 3 is equivalent to 60 degrees, in case you'd like to convert between them, sine of 60 is root 3 over 2, so we're looking at 3 root 3 over 2. Of course, the calculator will help you with that if you need or you want to verify it. Now, when we do the same sort of thing for g, we're going to end up with a quarter of the integral with pi in it, which in fact we've just calculated, so we know that already because we put in pi for one of these, minus the integral with a 2 pi in it. This is going to be slightly different. We need to replace these values with 2 pi. So theta becomes 2 pi, and instead of theta over 3, we get 2 pi over 3. This is starting to look a little bit messy. Shrink it down a little. But it does get simpler because, in fact, apart from this bit with the pi minus 3 root 3 over 2, this part here with the 2 pi minus 3 sine 2 pi by 3, sine 2 pi by 3, as you can verify in the calculator if you like, is the same as sine pi by 3. It's still just root 3 over 3. So we have a minus root 3 over root 3 over 2. We have minus 3 root 3 over 2 from there, and we're taking away minus 3 root 3 over 2 from here, and therefore they cancel out. The only thing that's left is the pi and the 2 pi. I've just realized what I've done wrong in this one. I've put pi into the wrong side. So it turns out we should have 2 pi there, 2 pi minus 3 sine 2 pi by 3. And over here, we've got pi minus 3 sine pi by 3, which, as we've said, we've already calculated. We know the value of that from here, but it turns out that sine pi by 3 and sine 2 pi by 3 are the same. And after that slightly garbled explanation, we have g equals a quarter of pi. So we can just write that as pi by 4. Now we've got a value for g. The last part here for b is going to be a similar sort of process, so I'm going to copy this across to make our life a bit easier. B is calculated by doing a quarter of. We need to sub in 3 pi into this side and 2 pi into this side. So I'll leave the 2 pi as is over there. This one's going to be 3. The difference here is that we have sine of 3 pi by 3. Sine pi, basically. And sine pi is 0, which means all of that stuff disappears, which will make our life a little bit easier. Sine 3 pi by 3 is nothing at all, so that's just 3 pi. And this bit, sine 2 pi by 3, we already know the value of. That's root 3 over 2. And when we simplify all of that, we get b equals a quarter of 3 pi minus 2 pi is pi, and we're adding 3 root 3 over 2 for this one. So it does end up looking quite similar to r. R is a quarter of pi minus 3 root 3 over 2. B is a quarter of pi plus 3 root 3 over 2, and g is just a quarter of pi. And at the end, we remember what we want to do. We can look back at what we said we needed to combine. The total area is given by this. So I can make use of what I worked out initially. The area is going to be 2 lots of that. And this is going to simplify down quite nicely, in fact, because r, a quarter of pi minus 3 root 3 over 2, when we add on b, which is a quarter of pi plus 3 root 3 over 2, things will cancel out quite well. And I'm going to take away g, which is just pi by 4. Now, as we said, things will cancel, so I don't need to multiply everything out to find out. I've got a quarter of minus 3 root 3 over 2, a quarter of plus 3 root 3 over 2, so all of those bits go. I've got a quarter of pi plus a quarter of pi minus a quarter of pi. So left behind here is just a quarter of pi, and that gives me pi by 2. That's the final area. Now, we want to double check what they're asking for precisely, because pi by 2 is all very well, but if, for instance, they said give your answer in square centimeters or something, they would have defined what r is measured in at the beginning. In this case, this is an abstract version, so there are no units for area. We can just say square units if you like, but we've got a precise value of pi by 2 for that area. The last thing you might want to do is a bit of a sense check. So this diagram, as you can see, is roughly to scale. It looks similar to the perfect version that I made over here already anyway. So you can rely on these as being reasonably accurate representations of what's going on, and you could even use it to do your estimate of the area. So for instance, because we know the greatest distance away for sine is 1, that happens not at 0 pi, 2 pi, but it happens at 3 pi when we've gone halfway around the entire curve. That gives a maximum possible radius of 1. Now the radius in the other direction is not quite so big. We'll get to that in part B because that will be relevant here. But if we assume that this whole thing is roughly the same as a circle of radius 1, then the whole thing would have an area of pi. And if we get an area of pi by 2, given that we're looking at this outer shaded section plus a bit in the middle, that seems reasonable. It's certainly plausible. It's within the bounds of possibility. So I'm happy with that for my answer for part A. Next, we have to look at part B. A copy of this logo is to be painted on a white wall of a building such that the total width of the logo is 12 meters. So from the left to the right hand side, we need 12 meters. Whereas in reality, we've got something else, depending on precisely how far away from the pole we are when we are as far away as possible, which is about here at 3 pi, and how far away we are when we're as close as possible, as far away as possible on the right, which is somewhere around here at 2 pi. But we'll get to that. The next thing after we scaled it up is to determine exactly how much paint we need. It says it has a minimum coverage of 30 square meters, and we need 2 coats of paint, and we need the minimum number of tins of paint that should be bought. So there'll be a bit of problem solving in the style of GCSE maths, really. How many tins of paint do you need to cover this after we've calculated the area? The one thing to watch out for here that you might be a little rusty on, depending on how much time you've spent on this type of problem or how much you thought about it when you first learned, this is area scale factors. We first need the width of the shape. Then we need to scale it up to a width of 12 meters. Then we need to scale up the area to determine the area of the larger shape. And that's going to involve an area scale factor. So we're going to watch out for that. I'll talk about that in a moment. First, let's deal with the width. The maximum distance to the left is 1. This occurs at theta equals 3 pi because we get sine of 3 pi over 6 or sine pi by 2, which is 1. So that's what's happening when we get to here-ish. Sine of 3 pi is going to give 1. The maximum distance to the right has got to happen at an even number. So it's obviously not at 0 pi, and it's not going to be at 1 pi because that's an odd number. But when we get all the way to 2 pi, that is the point we're interested in there. So the maximum distance to the right is sine of 2 pi by 6, which is just sine of pi by 3, which we probably remember by now. We've used this number a few times today, root 3 over 2. Therefore, the width, the total width of our shape is 1 plus root 3 over 2. And roughly speaking, We can double check with the calculator. 1 plus root 3 is this, divided by 2 is 1.3 something. So we've got a rough idea of what we're dealing with, 1.366. We need a width of 12 meters. So from our 1.366 units, we need to go up to 12 meters. The scale factor will be 12 divided by 1 plus root 3 over 2. So we can keep that nice and exact in there. And it's a little bit messy, but if need be, you can generate that as an exact value. You can do 12 divided by 1 plus root 3 over 2. That should deal with my brackets sensibly, and get a nice precise value if you want. Actually, we don't necessarily care about that, so I'm going to leave it in that current form, 12 over 1 plus 3 over 2. But you can see why 48 minus 24 root 3 would come out from that. You just need to do a bit of simplifying and rationalizing the denominator or the calculator. Once you've got your scale factor, we need the area scale factor. The simplest way to remember why these are not the same thing is to draw yourself a little square split into 4 squares and think about the length scale factor between the little squares that your square is split into and the larger ones. If you're, let's see if I can show it on here. Here we go. So if you pick a square made of 4 squares, the area is clearly 4 times the area of the smaller square, but the length is just double the length of the smaller square. And that's not just true for squares, it's true in general. So if you buy a 12-inch pizza instead of a 6-inch pizza, you're going to be getting 4 times as much pizza. And that's why typically they're going to cost a little bit more. That means the area scale factor we're going to get needs to be the square of this number. That's how we're going to be able to go directly from the area we've calculated of pi by 2 all the way to the true area. True area of the shape is going to be pi by 2 multiplied by our area scale factor. So from the calculator, we've got our scale factor for length. If I square it, I get the area scale factor, which the calculator is given up on surds at this point, but 41 point something. And then from there, we multiply by pi by 2. We don't need to worry about having lost precision at this point because we've turned it into a modeling question. We're now interested in how many tins of paint. So not only do we not particularly care about this being a multiple of pi or with appropriate radicals like root 3 in it, but in fact, all we really care about is how many tins of paint. At the end, it's going to be rounded so much that this detail is not going to matter. This is the area. And we need to go back and make sure we've interpreted the question properly and we know exactly how much goes in a tin. So it tells us that tins of colored paint have a minimum coverage of 30 square meters, and at 64.96 it looks like, well, we're going to need at least 2. We're going to want 3 because this wouldn't be enough. But then this is the detail I missed the first time I went through this. Given that 2 coats of paint will be needed, find the minimum number of tins of paint. So the coverage area of 30 square meters is for 1 coat. I think that's implied by this. Bit of a grey area depending on the tin, but generally speaking, that's what they'll be implying. So we can say since 2 coats are required, we'll be covering an area of 2 times 64.96 square meters. And that means, of course, we've got more like 130. And we can get the total number of tins required by dividing that number by 30 and then rounding up. We know we need to round up because this number will tell us exactly how many tins we're going to be using. But if we get a 4 point something, we know that means we'll need more than 4 tins. If we only bought 4 tins, we wouldn't have enough. If we buy 5 tins, we'll have about 2/3 of a tin left over. And now finally, we can do another little sense check there. The details you might miss in terms of extra coats of paint, that's something you'll need to read through the question to find. Our overall answer for the area that came out as about 60, we can check again. If we were told that the width was actually 12 meters, that makes for a radius of 6 meters. And if we look at the overall area, we do 6 squared times pi. That will give us the total area of the shape, 113. Remember, we're looking at something which we think is about half the area, so we can divide it by 2 and get 56-ish. Remember, our answer of 60-something is comparable to that. So we can be pretty confident that we've not messed up our area scale factor calculation.